Hello again. Good afternoon. So today we're going to cover lots of stuff. We're going to do some proofs, probably. But before I started, before we start talking about these things, I wanted to talk a little bit about the weekly reports. Now that report 0 is over and you know the basics of how to use LaTeX. So first of all, I should say that probably you should have started yesterday working on your weekly report for this Sunday. I think it would be a very bad idea to leave it to Friday and stuff like that, because you never know. You might get stuck at something, and often it's good in math to sleep on the problems that you're working on. You may not be able to solve them at first glance, and that doesn't mean that you can't do it. That means that your brain just needs to digest it and so on. And maybe we should first talk about your questions, and then I can say more things about these. You had some questions, yeah.
So the first thing I was going to ask about is what type of format do you want the citations for the bibliography?
Doesn't matter.
Doesn't matter, just having it.
As long as it's uniform, it's the same thing. Like there's a bunch of, the point I guess is that there's like MLA and some other, that doesn't matter as long as you use the same thing.
Okay.
Yeah.
And then so, this is a very general question, so if you give a general answer, I'm not going to be too angry about that. But how would you recommend us going about finding useful literature on topics we find interesting from the textbooks? Like if I saw some particular theorem that I found very interesting, and I want to go find more resources related to that, there's still enough citation distance one away from it.
Well, I mean, the first thing would be to look at Wikipedia, and like that probably has a bunch of things. Often the books themselves have like references listed in them. Especially, for instance, for Barnsley's book, if there's a theorem that Barnsley doesn't have the proof for, he says, oh, for the proof, see that. That doesn't mean that the proof that he refers to is going to make sense to you. Maybe there are like 7 other proofs and one of them is going to make more sense, but that's like a good starting point, I would say. Yeah.
Wonderful. Then my last question was, this is like once again pertaining a little bit more to citation distance. So
yes.
Citation distance to be of 1, should directly be citing the textbook, or is it more just
generally speaking,
an adjacent idea between the two things? That wouldn't take you like 4 different Wikipedia, boom, 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 boom.
Yeah. I mean, so I wrote that, but obviously I'm not going to be that strict about these kind of things.
Okay.
Right? My point is that I want you to, engage with the material, and like there's a lot of stuff you can do with it, and like, start thinking about things. That's the point. It's like I give exercises in the lectures, and it's about manipulating these definitions and so on. That's that. So there was this issue about like collectivity, and I don't want you to, the point is that I don't want 2 people to submit the same thing. And for that, I would highly recommend that you talk to each other, talk about what you guys are doing. But, even if you were to just focus on the Barnsley book, there are so many exercises in this that there's no reason for you to have any collisions. Like, so for instance, today we're going to be doing mostly section 3 in chapter 2. And this section itself has 21 exercises. That's a lot of exercises, right? So obviously some of them are harder than the other ones, but if you want to, if you're more advanced, like if you've seen LP spaces and stuff like that before, or LP distance, probably you don't want to sort of like verify that the LP distance is in fact the distance and so on. Just leave it to someone else that probably has seen this for the first time, and do other things. Okay. Regarding how to communicate, now I'm not going to regulate that whatsoever, so that's for you. My expectation is that in situations like this, often there is someone who's like more socially proactive, and that person sort of starts the conversation and so on. You can take your emails and stuff like that. There is a Discord server, I think. It's an unofficial server for the math department, and I checked today, there's a channel for 4800 that I didn't put there, but it is there and it's empty, so you can use that if you want. There's a bunch of things you can do. I'm not regulating that whatsoever, okay? So Oh, maybe I should talk a little bit about the audience. I sort of didn't say much about that in the specification document. You should think about, when you're sort of like thinking about the audience for your report, that should be some sort of idealized student who has taken this class, who has most of the prerequisites down. So it's like, if you need to sort of refer to some calculus idea, you don't need to go into sort of detail about that. You can assume that that person knows the background, but some of you are more sort of in other science fields or applied. So it's like if you're trying to come up with, or if you're trying to say something about some specific chemical process, you would need to define the terms. Okay, I'm talking to you, of course, but especially in the Schroeder book, I'm reading that popular science book that I suggested. There's a bunch of things, and it's like coagulation, blah, blah, blah. It's like, I don't know these terms, okay? So you need, like, if you might know these things, but your audience doesn't know these kind of things, so you would need to define them. And of course, this is good because that sort of like extends your report. Because if you try to be concise, obviously filling out 2 pages is going to be harder. Another thing, I wrote that in the report, but I want to mention again, I don't want you to say, I'm doing this exercise from that thing. Like, I don't just write the whole exercise. I don't want to chase what you're referring to, which edition you're referring to, write it there. So one example I have is, for instance, in section 3 here, there's an exercise, which is 3.8. It says, let x1 d1 and x2 d2 be equivalent metric spaces. Suppose x1 d1 is complete. Show that x2 d2 is complete. Okay. So completeness we're going to discuss today. But so I don't want you to say, when you're writing the report, I'm solving right now exercise 3.8 on this page. I want you to, write that, but on top of that, write the exercise, the statement of it, so that I know what you're doing. And immediately you should say something like, oh, in the book it says equivalent metric spaces, but in class we talked about a couple of different kinds of equivalences. So what exactly is Barnsley talking about? So that's why you need to sort of, you're going to have to read what comes before to understand what exactly he means. In this case, he means Lipschitz equivalent in our language. But I'm just warning you because there are, obviously, like, depending on the context, different people call the same things different things, or vice versa. So that's that. Any questions about these? And as time goes by, I think we're going to understand this more and more, and hopefully it's going to work. So, and if not, I'm also like open to changing the policies a little bit and so on, so that it works better. Okay? Any questions about these things? I should also mention that probably you should also be in constant communication with me, sending emails, asking for meetings and stuff like that, so that we can discuss. So it should be normal. It should be natural. Like the class is advanced, obviously, and I'm taking it even more beyond sort of what is in the book. So if you're sort of like breezing through everything, probably you're doing it wrong. Okay, so and I'm there to help you. Okay. Any questions about any of this stuff? Yes.
It's kind of what we talked about last class period. I'm just curious, like, what the value in having the Holder continuity definition, like, where does it get used for anything,
I guess? It is used in dynamics a lot. So Holder or Holder continuity is a worse version of Lipschitz continuity. It's better than continuous, okay? That's the point. And it's almost like, so when you're talking about the theta Holder function, you should think of it as theta differentiable, like 1/2 differentiable function. It's like, it's better than continuous. That's what. Okay. So this is too advanced for this class, but there's so in what is called hyperbolic dynamics, there was a big issue about something called ergodicity. We're going to see this word a little bit as well. of certain systems. And so for that, what you do is you have a dynamical system, which we're going to discuss later too, but it's a transformation acting on a space, okay? And to it, you associate certain what are called manifolds. These are stable manifolds, unstable manifolds, and so on. But it turns out that these stable manifolds and unstable manifolds are not very nice. They're not as bad as fractals, but still they're not as nice as you want them to be. But somehow this Hölder property allows you to sort of still work with things. Let's put it that way. So that's one reason. Another reason is when we start talking about dimensions of things, we're going to learn, rigorously, we're going to learn that most notions of dimensions are going to be invariant under bi-Lipschitz maps. Because you may as well imagine that bi-Lipschitz is basically differentiable, and so if I want to do a change of coordinates in the sense of like, U substitution or something, you need the derivative. Okay, even if you don't have derivative, Lipschitz means you basically have the derivative. This is like slightly worse of a version of that. Yeah, it just shows up in nature or in dynamics very naturally. Yeah. Any other questions? Okay.
This definition is, maybe I wasn't paying attention well enough to that question about there being three different sort of.
Yeah. I will go through that now. This is like what I wanted to start with. Okay. So a couple more definitions. These are really sort of part of last week's stuff, but still. I'm going to call a function from x to y, and recall that when I write it like this, I mean this symmetric space is symmetric space. I don't write the d's and so on. I'm not like being formal as I am over here, but you're supposed to imagine that these are metric spaces. I'm going to call it a homeomorphism if it is continuous, invertible, so there's an F inverse map from here to there, and F inverse 2 is continuous. So this is sort of one of the basic ideas of what is called topology. It's an area that is more general than metric spaces. And you have these adjectives: bi-uniform homeomorphism, bi-Lipschitz homeomorphism, bi-Hölder homeomorphism. Well, if it's a homeomorphism and both F and F inverse are uniformly continuous, or Lipschitz or Hölder. And then more notions of equivalence for metrics. If I have a set X and two distance functions d1 and d2 on X, I'm going to call them topologically, uniformly, bi-Lipschitz or bi-Hölder equivalent based on the properties of the identity map. I think we had given the definition for bi-Lipschitz. I'm just generalizing this. Okay. So what does it mean, for instance, for two distances to be topologically equivalent? That means that I want the identity map from here to there to be continuous, and from here to there to be continuous. And if I want it to be uniformly equivalent to distances, I want identity to be uniformly continuous this way, and so on. This is just some terminology. Okay, so some examples. So today we're going to start talking about this topological structure of a metric space as well as the uniform structure of a metric space. These are two distinct things. And for that, it turns out that using certain sets related to the distance function becomes important. So let's now focus on this. So let X be a set, and let D be a metric on it. Be a metric on it. So that means that D takes two inputs from X and produces a number which is a distance between them on it. Let's also fix some point X, okay? Or let's say X0. Now, if I feed only this point to D, now I would have this. And I'm going to write it like this. So in the first entry, I plugged in x0. Second entry, I leave it as empty. And so now this is a function from x to non-negative numbers. Okay? So what does this function do? It takes a point x and gives back the distance of that point to this fixed point x0. Now I claim that this function is continuous. Okay? And in fact, let's do more. This function is Lipschitz. Okay. So let's write it out. What does this mean? So this is my new function. Okay. So if you want, you can call this f of x if this is x. So I want something like this, right? So no. And of course here I'm using the standard Euclidean metric. These are the two values of this function at x and y. Now I'm taking the absolute value. I want this to be bounded by some number times, let's write it, c times distance, let me not write it, of x and y. Okay? This inequality, so for any x and y, this inequality is equivalent to saying that this function right here is Lipschitz. Okay? I want this. Okay? But let's think about this then. So let me just take this expression. So in this generality, all you have is that this is a metric, which means that ultimately you should be using the triangular inequality. You're seeing three points, and somehow you need to sort of like move that triangular inequality in such a way that you get this thing, right? So what I can do is this. If I were to start with this expression, well, this is by the triangular inequality, right? If I were to plug in y to this, I would get something else. Okay, I just use a triangular inequality. And here I also use the symmetry property, right? Because distance from x to y is the same thing as distance from y to x. Okay, well, this is a non-negative number. I can take it to the other side. We're almost there. Okay, so you can do this, or you can start with d of x0, y here, and then put in x here. Maybe I should write it. So similarly, x0, y by the triangular inequality dominated by this, which then I can again take this to the other side. 0, so let me write it like this. Minus plus d 0 y. Okay. I just replaced interchanged the positions of x and y basically here. The point here is that this, of course, is nothing but minus this expression on the left-hand side? Well, I'm saying that whatever this value is, d of x comma y, it is larger than both this number and minus the same number. That's equivalent to saying that this number is more than the absolute value of that number. Okay? And this was what I was trying to show, as you see. So once you have a metric on a set, it becomes continuous relative to itself. Okay? Any questions about this? Yes?
Yeah, I'm a little intrigued about how this specifically applies continuity. Does it imply continuity because,
Oh, okay.
Because it is Lipschitz? Or
Well, yes, Lipschitz,
okay.
that was an exercise from last week. Lipschitz means,
Implies continuity, right?
yes,
So-
and in fact, it implies uniform continuity.
So, I'm trying to find a definition of Lipschitz just because I want to check my knowledge specifically on this. So it's almost sort of like you're treating this d of x naught comma x minus d of x naught comma y more as that function where you're inputting two things.
Yeah, let's write it like this. So this is what I'm trying to think of.
Okay.
Okay?
I'll write that down real quick. That answers my questions. Thank you.
Okay, good. So now let's take this one step further. And so this, it's an intuitive thing that it is basically continuous because, when so if you were to fix a point in space and if you were to move some other point around it, well, the distance should depend continuously, basically, right? That's sort of like an intuitive idea. And as you see, it follows immediately from, or basically from the triangular inequality. This somehow is a thing. It's the axiom that makes it work. Oh. Not only do I want distances between points, but distances between a set and a point. So that's a definition. Metric space for any x in x, it's a point, and for any subset A in x, define now I'm overloading this d. I'm going to say d of x comma a. This is a new thing. Okay, I'm going to define it like this. So maybe I should draw a picture. So you should imagine it like this. I have a here, and I have a point here. Of course, it might be inside and so on, but we're going to see. So how can I define the distance between these two things? It basically should be this, okay? Now, how do you formalize it? Well, you say, take any point in A. A has a bunch of points in it. Look at this distance. Well, minimize that distance. So here I'm going to use this infimum, okay? Infimum of d of x comma a, where lowercase a varies in uppercase a. Recall that infimum is basically minimum, except that the boundary of a may not be included in a, so maybe it could be an open interval or something, and so that sort of like makes it formal. So this is basically minimum. Okay. Any questions about this? This is the distance between x and a set, a point and a set. Well, there's one issue. What if A is empty? Okay. If A were empty, okay, so maybe we should think about this a little bit. So another way of writing this is this. Infimum of a certain set, a certain subset of real numbers, which is this. Okay, this is a set. It's a subset of the real numbers. Let's say that there's this, then a couple of these, and this one. And you're looking at the minimum of this. But if this set, this A, is empty, that means that this set is empty. But what is the infimum of the empty set? What is the minimum of something that doesn't exist? Well, it turns out that some people say it doesn't exist. For us, it would be infinite. Because if there's nothing here, the sort of like the lower bound would run all the way to infinity. There's nothing that's stopping this lower bound. Okay, that's the idea. And so that's why typically you want capital A to be non-empty. So obviously this is like a silly mathematical thing, but at least when you're first learning these kind of things, it's good to think about them. Okay, now it turns out that this too is continuous. Basically, using the same idea, that's going to be an exercise.
So does the A being empty not count as a discontinuity?
No. I'm saying for fixed A.
Oh.
I fix A, vary X. For any A non-empty, this is Lipschitz. It's basically what we just did about the continuity of the D function, but you're going to have to do something more to handle this infimum over here. Another exercise. In fact, I don't need to fix anything inside D. This function is also continuous, okay? Now, what does that mean? Well, I should have some sort of a metric on this product space. Well, one thing you can do is this. You can say that the distance on this product set is this, right? So I need to say something about the distance between pairs of points. So x1, y1, comma x2, y2. There are multiple ways of doing this. Let's just say that this is the same thing as the distance between the first coordinates plus the distance between the second coordinates. And of course, perhaps I should also put that as an exercise. That's a metric. Which means that it's a function from x times x times x times x to the non-negative numbers, and so on. Okay? Okay, so.
Can I ask a question about that one?
Yes.
Since we're including infinity in our codomain of D,
Yes.
I'm sure we're not going to be proving the continuity like this, but what would be, like, would infinity be an open set in the extended real numbers, or, like, I guess, how would we include, what sets would we call open when we include infinity in all?
That's an exercise for you. But let me just say it like this. So first of all, if A were not empty set, this would be a finite number. Okay? Now this infinity situation happens if you want to allow the empty set as one of these inputs. In that case, I would write that as taking values in, instead of writing it like this, I would write it like this. So I would like to imagine that this is basically like a closed interval. So that's enough hint, I think. Yeah. Okay. Okay, label sets of metrics. And by this I mean things like balls, spheres, and so on. So you have this set, you have a metric on it. And one thing, so that's like the fundamental function on that space. You should think of it like that. The metric, on the one hand, gives structure to the space. On the other hand, is basically just like any other function on it. So you can sort of like think of the metric both ways. There are many other ways of thinking about the metric, but that's two ways. So the most important, perhaps, version is this, an open ball of radius r. It's a positive number centered at x. And I'm going to introduce a notation that is not very common. I'm going to write it like this. This is my notation for the open ball. And by definition, it is this set. It is a set of all those points, y in x, such that y is at most, or not more than r distant from x. Other common notations for this are like some people write b of x comma r, or b sub r of x, or they write u of x comma r. There are many notations for this. This is what I'm going to use because it's more uniform, let's say. And as you can imagine, in the case of Rn, or R3, let's say, if I were to use the L2 distance, that would be exactly the ball that you would imagine. Okay, that's what I'm saying. Everything inside is included. The boundary is not included. Okay, closed ball, so this is open. Closed ball if you include the sphere around it as well. And I'm going to denote it like this. So in this notation, here I put the center, and here I put whatever I want for the radii. And then sphere, well, I would just write it like this. Okay, now I hope you get the idea. This goes over there. Now I draw things like this, but in this abstract context, as you can imagine, these make sense, but they need not look like this. Okay. So one good example, one good exercise will be this. What are open balls, closed balls, and spheres relative to discrete metric? What do these look like, let's say? Relative to the discrete metric.
a sphere is just the border?
Yes, it's the border, exactly. Yeah. And if I want to be more specific, more explicit, I could also write it like this, right? So I would say this, but really I mean this. X comma D, that's my space. Okay. If you want to be more explicit, that's sort of how the notation sort of changes. The reason, and so for instance, for spheres, you might use S and stuff like that. The reason I use sort of this type of notation is that once you have like 7 different spaces in like 15 different metrics, it becomes sort of complicated to sort of figure out what exactly you're referring to and so on. Okay?
So I think I'm still a little confused about what this exercise is really trying to prove or what you're trying to look into here. With what you used to mean, what does it look like relative to a discrete metric?
What are these? I mean, yeah. So look like here means that it's the same look like when I say for R2, if I were to use the L2 distance, a closed ball of radius r would literally be a disk of radius r. So okay, so I can imagine it like that. So that's exactly what it would look like. But if you had a discrete metric, how does that look like? It's going to be a bunch of points, of course, but how many, for instance?
Okay. I think I see the question.
Yeah. Yeah. So recall that for discrete metric, if you're using discrete metric, the distance between any 2 distinct points is 1. Which means that if you were to take a ball of radius 2, you would have everything in the space included in the ball. On the other hand, if you were to take a ball of radius 1/2, that ball actually looks like a point, which is the center. That's sort of my idea. Okay. So when we're talking about distances and metrics and so on, that's sort of like a metaphorical idea in a sense. But somehow, that should really affect the way you're thinking about the object geometrically. Okay, again, let's take this one step further. I want to do the same thing where instead of a point here, I have a subset. Okay. These don't exactly have names, but this notation still makes sense. So now I take a subset and a non-negative number or positive number. And let's say that I want to make sense of this. Sort of like the open ball around A of radius r. Well, what could that mean? Well, if this is my A, what I want to do is I want to sort of expand it by r. Okay, that's the idea. This is that. Well, how can I write this? Well, one of the things I can do is I can take the union of all the balls whose centers are in A. Okay, that's one thing. Or you can say this is the set of all those points that are not more than r distant to some point in A. Not that are at most, that are less than r distant to some point in A. Okay. So what you can do is on the Euclidean space R2, let's say, you take a letter, that's a set after all, by taking an R neighborhood of it, that's another word, neighborhood, you're sort of turning that letter into something more, bulbous, let's say. So, example. This turns into, if you have this, now it's like this. Okay. That is, if this is A, this is this. And of course, as you increase R, for instance, eventually this hole is going to disappear, and you're going to start growing and growing. And in fact, this is what Ravi Vakil calls doodling. On Canvas, I populated the files folder with a bunch of papers and like references and so on that you might have a look at. So there's a paper by Vakil about basically this stuff. If you want to have a look at that or think about it, you're good to go. And there's a bunch of talks that he gave about this. It's accessible for undergrads. So, okay. Now later on, this is going to being able to go from here to there is going to come in handy when we try to come up with a distance between two sets. Because it turns out, how are these related to iterated function systems and fractals? What we want to say is something like, oh, the Cantor set, or this iterative procedure, where you start like this, and then you get the middle third so that you have this, and then you get the middle third of that, you get this, and so on. You get the Cantor set at the end. We want to say something like, this sequence of sets converges to this. And for that, we're going to have to use some notion, which is this Hausdorff distance, that uses this idea. I'm not going to go any further now, because next week is going to be all about this Hausdorff distance. It takes a while to get accustomed to this idea, but it's very useful. Any questions about these so far? Okay. So now let's talk about sequences. We had already seen sequences in the context of shift spaces, but sequences turns out to be useful in sort of like general situations as well. I'm going to denote it like this. X, I'm going to put a bullet here. It's like the placeholder, and by a sequence I just mean it's going to be a function going from integers to my space, and typically you would see these sorts of notations. So this is like common x sub n in parens, or maybe there's like an n here, or x sub n in curly braces, and then it says n from 0 to infinity. There's a bunch of different ways of writing this. I'm just going to write it like this. Okay, subsequence. So that's a sequence. Subsequence. It's going to be a sequence that is basically a sequence that you obtain by sampling some of the times here. I'd like to imagine this as time, and I'd like to imagine that if this is my x, capital X, this is sort of like my time parameter. At time 0, I was at x sub 0, and then time 1, I went to x sub 1. And then at time 2, I went to x sub 2, sorry, and so on. For a subsequence, what you do is you sample some of these states, except that you get to skip a couple. And further, you want to keep the same future. Okay? So I'm going to say that this is a subsequence, x dot prime is a subsequence, that's my notation. So is a subsequence that's how I say it. If there's an increasing function let's say I from integers to itself such that, so this is my sampling function if you want, x prime at time n is really x at time I of n. Okay, so here's an example. So for instance, I can take a sequence of numbers, right? That's sort of where we start at. Let's say that x sub n is minus 1 to the n. That's a sequence in real numbers, or integers if you want. So sequence. So how can I imagine this? Well, n is sort of like my discrete time. And so I might as well graph this like this. So depending on the oddity of n, my time, I get either +1 or -1. So this is a sequence that alternates between +1 or -1. Okay? 1, -1. So if I were to start at 0, x sub 0 is -1 to the 0, that's 1. Let's draw these times as well. What is x sub 1? Well, x sub 1 is -1 to the 1, that is -1. X sub 2 is -1 to the 2, and so on. Okay? A subsequence would be, one of the subsequences I can take is, let's say, so that's, this is x bullet, if you want. And then my subsequence could be, for instance, like this. I'm just going to write it on x prime at time 0. So I'm sampling, but I have to go forward. X prime at time 1. You see, I skipped this. I said I'm going to take this guy next. And then I'm going to skip this, for instance, and I'm going to take this. And so on. So one could write x prime n is -1. Well, how can I write it? Well, that should be something like -1 to the 2n, right? Which is the same thing as just 1, of course, but that's the idea. Now, one nice thing about this is that, as you can see here, even though x, the original, or x bullet, the original sequence does not converge to anything, it keeps oscillating, this particular subsequence does converge, which is because it's a constant sequence after all. So now let's sort of incorporate this notion of convergence. We're going to say that a sequence converges definition. to, let's say, some limits. You see, now we're incorporating these ideas of limit and stuff. So let's say x sub infinity, at time infinity, that's my limit. If for any epsilon positive, there's an integer capital N, such that for any lowercase n, after capital N, I have this. Okay, now what does this mean? My sequence is a bunch of points, and there's a time parameter that I have. x1, x2, x3, and so on. Keeps moving around in the space. And I have this target. Okay? Convergence means the following. You have your target. Somehow you came up with this target. You say, I want to go there. But instead of saying, I want to hit exactly this, you say, let me try to approximate it. Okay? I'm going to try to approximate x sub infinity, that's my target point, by a margin of epsilon. So that means that I'm taking a ball around it. This statement says the following. Once I choose my error margin, there is some time n such that after that time, my sequence keeps hitting this ball. Okay? I don't care initially what happens. The sequence might sort of like go to bizarre places. Let's say that you started here, you go this way, come back, blah, blah, blah. And then once you wait long enough, you keep hitting here. Okay? But you want to be able to do this for any epsilon. So let's say that you were able to do this for epsilon equals 1. Okay? So that was fine. Now you want to do it for epsilon equals 1 over 2. So now you're being more restrictive. If you can still do the same thing with possibly a different n, that's still good. Now you do it for epsilon equals 1 over 3 and so on. You keep shrinking this target, but convergence means that no matter how small your target is, if you wait long enough, you're going to end up in that ball. That's the idea. Okay? Any questions about this? Okay, let's take a 5-minute break. Now, here's some logical stuff. Oh, before that, I should mention this is also the notation. If you want to be concise, you just write x bullet arrow x infinity. That means convergent, or you can just use a standard calculus notation. Limit as n goes to infinity of x sub n equals x infinity. These are all the same things. I also wanted to introduce some further logic because in this class, one of the important things is going to be taking statements like the statement for convergence and turning it into sets, basically. So here's one way of doing this. This convergence, x bullet converging to x infinity, is equivalent to this. Okay? I then change the quantifiers. Instead of writing the distance between xn and x infinity is less than epsilon, I just said, oh, the x infinity point is in the epsilon ball of xn. Okay? So now I'm changing the perspective a little bit. Instead of thinking this original way, where you have this target and you keep hitting it after some finite time, I'm saying that x infinity hits the ball of the thing that moves. That's sort of like another way of saying this, but it's logically equivalent. Yet another way of saying this is that instead of saying epsilon, it's a positive number, positive real number, that could be pi, 1 over pi, and so on, we can use only integers. That's the only difference I make here, from here to there. I'm saying for any integer k, well, I can just say, instead of epsilon, I'm going to use 1 over k. So that means that it should be less than 1, it should be less than 1 over 2, or maybe I should put here at least 1, so that it makes sense. So this distance should be less than 1, 1 over 2, 1 over 3, and so on. Now here is the step where I really turn this into a set, I want to say that x infinity is in a certain set. And I want to make the setup using these, I want to set up the set using these balls, basically, and these quantifiers. The main idea is that whenever you have a for all, that corresponds to an intersection. And whenever you have exists, that corresponds to a union. Okay, that's the idea. Intersection. So what I can say is this. This is equivalent to saying that x infinity is in this ball for any n. So that means that I need to intersect these guys. But I need to wait for n time. What is n? I don't care what n is, as long as there is one, which means that I need to have a union. Okay. For which k? I don't care. Well, I need it for any k. Okay. So that's an intersection. Saying convergent, so x bullet converges to x infinity, is logically equivalent to saying that this point belongs to this set. What is this set? It's a weird set, but one thing that you should look at here is that it's a bunch of balls. Okay, these are level sets of the distance function. That's nice. And then there's a bunch of intersections and unions and so on. But what is nice is that these intersections and unions are over integers. Okay, that's going to be important later. We're going to call these sets measurable, or rather Borel measurable later on. So. At this point, obviously, this is like overkill in a sense. It doesn't really help that much, switching from here to there. But you might imagine something like this. You're going to have a statement. It says blah, blah, blah. And you want to think about how common that situation is, that statement is. And so if you can turn that statement into a set, you can now talk about its measure or volume or dimension, if you want. Okay, so that's going to be important for us. So this is, for instance, one way you start using ideas like dimension and measure in the context of number theory. Okay, any questions about these conversions and stuff like that? Of course, the beauty here is that you can think about these things geometrically. X bullet converges to x infinity, like I described here, or you can turn it into pure logic, and that's very powerful. Now here's an exercise. Convergent sequences gives you another way of thinking about continuity, which perhaps is much more manageable, because now you have time, everything is discrete in a sense. A function is continuous using the epsilon delta definition. If and only if, which means it goes both ways. This is the same thing as this. It's logically equivalent. F takes any convergent sequence in X to some convergent sequence in Y. Okay. This is a very good exercise if you haven't seen this before. I mean, it's still a good exercise if you have seen it, but probably you want to leave it to someone who haven't thought about this before. Okay. That's good. So often, that means that after this exercise, if you have continuity, or if you're worried about the continuity of something, okay, Lipschitz conditions and stuff like that, it's not as straightforward as this, but if you're only worried about continuity, all you can do is, or one of the things you can do is, you can take a sequence that converges and see what the image does. Okay. Or, you know, if I want to write it like this, I would say in calculus notation, right? Limit as n goes to infinity of f sub x sub n, f of x sub n equals f of limit s, which is the same thing as this, of course. It's the same thing. Okay. How many of you have seen something like this before? At least in calculus, let's say. Maybe, okay. The ideas are sort of familiar. Okay, good. Now, another type of sequence is called Cauchy. Because as you can see here, when you're talking about convergence of a sequence, you really need this guy. You can just take a sequence, and if you're starting to talk about convergence of it, well, you need a target. Cauchy allows you to talk about sequences without looking at the target. Okay. And how do you do this? You say, so that's the definition. Your sequence x bullet is Cauchy if instead of saying it reaches to that target over there because you don't have access to that target, quite possibly, you say after finite time, the sequence doesn't move that much. So now you want to compare xn to some other time. Let's say xn to xm. X bullet is Cauchy. That's another person who was really into these kind of things back in the day. I mean, he was one of the founders probably. If for any epsilon there is an n integer such that for any lowercase n after capital N and for any p integer arbitrary, the distance between x sub n and x sub n plus p is less than epsilon. Okay, now let's think about this. That says that I take an error margin epsilon. Then I get to wait some amount of time, n. After waiting n steps, okay, now lowercase is capital N or capital N plus 1, I don't care what, but it's after n. And if I were to shift the time by p, so that I'm comparing the distance between x sub n, so what happens at time n, and what happens at time n plus p. I'm saying that this shouldn't be too different from each other for any epsilon. Okay? Then you call it Cauchy. Now it turns out that convergence sequences are Cauchy. Let's perhaps prove this. Proposition if I have a convergence sequence, then X bullet is Cauchy. Proof. Now, what's the idea? Let's first draw pictures. I have a sequence, and I have a target x infinity, and I know that x bullet, my sequence converges to x infinity. That means that if I were to take some epsilon, and if I were to wait some time, this is what definition of convergence says, well, I'm going to keep hitting the epsilon ball centered at x infinity. But let's do it slightly differently. Instead of using epsilon as my error margin, let me use epsilon over 2. You're going to see in a second why. There's an n such that this is like a faster way of writing this expression. That's by definition of convergence. Now I want to compare xn to xn plus p. Okay? Oh, sorry. I want to say epsilon over 2. Let's say that I take p positive. Well, I know that x sub n plus p, 2 is going to be in this ball. Now, any ideas as to how I can get to the distance between this guy and this guy, as in this expression? Yes? That's the one thing you have, right? Like there's nothing else here. So, okay, the distance between x sub n and x sub n plus 1 is dominated by the sum of these two distances. This is not more than epsilon over 2, and this 2 is, which means that in total, this is bounded by epsilon. Okay? Which means that indeed it is Cauchy. And what is the picture? The picture perhaps is more obvious. I'm saying take epsilon, and instead of using epsilon as your error margin, use epsilon over 2. If I wait some time, I know that I'm going to keep hitting this ball. Well, I'm saying that if both of these have to be epsilon over 2 close to x infinity, well, the distance between these two cannot be more than, what is this, the diameter. Okay, that's the idea. And the diameter of this, of course, is epsilon. Does this make sense? These are like simple, like logical tricks, but they are very powerful. Any questions about this?
So when people are like solving these for like the first time, do they just, is it common for like them to just use epsilon and then they get 2 epsilon?
Exactly. Yeah, that's how I did it. In reality, like if you want to, so like getting epsilon here is sort of like a stylistic thing. You can say take epsilon and then, so that after finite time I have this, and then if you were to apply the same thing, you would get 2 epsilon here. If you want to get epsilon here, then you have to halve it here. Okay. Exactly.
Are you okay with like any
Yes.
function of epsilon?
Yes.
Our answers?
Yes. I mean, this is not the class where this is the main focus. So, as long as I understand what you're doing. And you don't need to be this formal too. It's like, so if this were like an exercise that you were submitting, probably you could write it like this, right? If you wanted. There's an epsilon, there's an n such that this, and then this happens, and then don't write this, and don't write this, and then this is 2 epsilon. So this is also sort of like a valid way, and you can even go like more minimalistic, but I'm asking you to at least use full sentences and everything. Okay, I mean that's for your benefit, but if ideas are new to you, probably you want to sort of be more clear so that you're aware of what you're doing and so on. If you've done this like 7 billion times, then obviously you don't need to write everything. But then again, probably you shouldn't be doing that as an exercise in your report. Okay, so that's convergence sequence, Cauchy sequence. Convergence implies Cauchy. How about the other way around? It turns out that the other way around is not quite correct. And in fact, that becomes a definition.
Only in R, right? To go back the other way from Cauchy to convergence. Or sorry, convergence. Yeah, Cauchy.
By R, you mean a complete metric space?
Yeah.
Yes.
So, yeah.
Yes. A metric space is complete if any Cauchy sequence is convergent. Now, why would this be a nice definition? Because, maybe you have a sequence and you want to say, oh, this sequence converges to that. But what is the target? You don't know what the target is, quite possibly. Well, if your space is complete, all you can do, or one of the things you can do is to say that, or to verify that it's Cauchy. Then, by definition, that says that there's a limit. You don't know what the limit is, but at least you know that it exists. Okay? And in fact, it's going to turn out that the space of fractals is what Barnsley says, is a complete metric space. And when we have an iterated function system, the different sets you get at different stages turns out to be a Cauchy sequence. And the limit, the Cantor set type of thing, is going to be that target. Okay? We're going to spend a lot of time next week showing that space of, maybe not too much time, but we're going to spend some time. We're going to showing that the space of fractals is a complete metric space, so that this works. And of course, what is the most important example? It's the example that your colleague mentioned. Real numbers is complete. Rational numbers in it is not complete. That's the idea. Rational numbers. That's an exercise, actually. Is not complete. One final thing about this. The way to think about this is like this. If I were to take a real number, it is a decimal expansion. Okay? Take pi, it is 3.141 something something. The point is that a number is rational if and only if eventually you start repeating. This is irrational, which means that this expansion does not repeat. Still, what you can do is you can take, the first one decimal, and then 2 decimals, and then 3 decimals, and so on. That would give you a sequence. That's your first element in the sequence. That's the second element. That's the third element, and so on. That would give you a sequence in the rational numbers. You can see that it is. You can show that it is Cauchy, because after finite time, right, the different values of your sequence vary up to an order of magnitude. But the limit is not in Q, because the limit is irrational. Limit is in R though. That's the point. Okay? This is the example to think about. Okay? Good. I think it's time for today. I'll see you on Thursday. Okay, let's start. Hello, good afternoon, or yeah, good noon. So today we're going to take things up a notch. We're going to have a bunch of definitions, basically some of these words that we need from this topological box that I wrote. And we're going to have our first proof of a legitimate important theorem. That's going to probably take a while. So I just wanted to mention this. At this point, we've already seen a bunch of phrases, names, and stuff like that. And I wanted to mention how these different names really belong to different contexts. Okay? And so we have a couple of them, and these are the sort of important ones for us. So these are the different contexts. Technically, these are categories, and there's like a whole theory of what it means for something to be a category mathematically, or what it means for something to be a context, but we're not going to get into that. All you need is this understanding. And you should think of it like this. As you're going up, things are getting more important and better. They become more regular. At first, you have the set context. And so words like cardinality, number of elements, one-to-one, onto, bijection, these type of things are related to sets. And once a phrase is admissible in one category, it's admissible in this category as well. So things get more specialized, basically. And then you have the measurable context. We're going to spend a lot of time toward the end of this class about this. Lebesgue measure we saw already. Integrals, probability, randomness, these kind of things come from this measurable category. Then we have the topological category. When you start talking about sequences converging, continuity, open, closed sets, compactness, or compact sets, connected sets, path-connected sets. These are all in this topological category. The important thing here is that you see, for instance, uniform continuity, even though I gave the definition of continuity and uniform continuity basically at the same time, they actually belong to different contexts. So in the uniform context, you have Cauchy sequences. Likewise, Cauchy sequence is something more specific. It belongs to a more specific context than just a convergent sequence. And completeness too. These are, again, they all belong to the uniform category. Next up is what I said, rough, smooth. Lipschitz, Hölder, continuity. These are basically differentiability conditions, like we discussed. And the notions of dimension that we're going to discuss later, when we start talking about dimension theory too, they really belong to this. And even beyond that is the actual differentiable or continuously differentiable, twice continuously differentiable, or infinitely many times continuously differentiable. These belong to the smooth category. Okay. And I wanted to say also, so this is the taxonomy of how you name things. In each of these contexts, you have one notion of sameness. Okay. So what it means for two things to be isomorphic, or isomorphism. Well, in the case of sets, you call two sets isomorphic. They are the same thing. They don't have anything else but cardinality, the number of things, if there's a bijection between them. Measurable, you call it bimeasurable or measurable automorphism. Let me not write that. It's not super nice, and we don't need it for now. In the topological context, what is the name? We learned the name for that. Exactly. Homeomorphism is basically two things being same in the context of topology. Here, we said bi-uniform homeomorphism. Sometimes people call it uniform isomorphism as well. Here, bi-Lipschitz, bi-Hölder homeomorphisms, they really belong here. Let me not write it. And then here, we're probably not going to use this too much, but still it's good to know. The word for isomorphism in the context of differentiability, when you have like differentiable objects, is called a diffeomorphism. So it's the same differentiable structure. Okay? And here's an exercise. What is most important here, at least for us, is a distinction between these two. Okay? And this exercise is about that.
Can I ask a question?
Yes.
So I'm looking for, I guess, where metrizability might fit in these categories.
Yeah.
In between topological and uniform, or is it the same as uniform?
It's beyond uniform. Yeah. Yeah. Any. So there's something called a uniform space, where you have something called a uniformity on a space, and any metric space has a uniformity, but not vice versa, I believe. Yeah. And again, there's like a more general context of what it means for something to be a topological space. And then back in the beginning of last century, people were very interested in this question. Oh, I take a topological space, and we're going to see this today. Topological spaces are basically characterized by what it means for things to be open somehow. So you have these axioms, and given this topological space, is there a metric on it that basically gives this notion of openness, or this notion of continuity? At this point, it is fairly classical, and it's basically done. It's an area that is not that interesting for most people, but still, metrization problems is important. Maybe we'll discuss something about that eventually. Any other questions? Okay. Exercise. So last time we said we had this notion of continuity for functions using epsilon delta, and then I gave a definition or an equivalent characterization of continuity using convergent sequences. I said a function is continuous if and only if it takes convergent sequences to convergent sequences. And then you may want to ask for the same thing when it comes to Cauchy and uniform continuity. And it turns out that to some extent it is true that if you have a function from x to y, two metric spaces, and if it is uniformly continuous, then it preserves Cauchy sequences. X bullet Cauchy in X. Recall that Cauchy means that you're sort of going around in X. And I'm saying that if you wait finite time, after that finite time, your points will not be too distant from each other. So let me write it like this. For any Cauchy in X, the image sequence is Cauchy in Y. So that's sort of some evidence as to why these two should be in the same category. And indeed, if you had a function that is only continuous, it doesn't mean that it's going to preserve Cauchyness. If f is merely continuous, it may not preserve Cauchyness. I don't know if that's a word, but it is now. And another thing you can ask, is this two two ways. So is this a characterization? It turns out it is not. And so another exercise. Not vice versa. And I mean this. Okay. It's a nice thing. Okay. And of course, the point is that all of these categories sort of interact with each other in mysterious ways, let's say, and the point is to understand them. As is common in Western science, we try to understand something, and to understand it, you sort of like split it into pieces, and then if we realize it's now more complicated and makes less sense. But anyway, any questions about these? Okay. So now we're going to focus on these words: open, closed, compact, bounded, totally bounded, a bunch of other things. And let me also say that each of these words, if you're taking a topology class, let's say, they probably spend around like 2 weeks for each and every single one of these words. So if this is the first time you're seeing these, and I'm expecting that most of you are, it's not a problem that you're struggling with things. So if you're struggling, then that's good. I am front-loading the terminology, and throughout this semester, we're going to get more comfortable with it. That is like one of the major handicaps about learning dynamics, because it's not a fundamental field. And to start doing dynamics, you need a bunch of other terminology from other fields of mathematics, from other disciplines. And so this is sort of true in, more generally in mathematical physics, probably, even though dynamics is not exactly mathematical physics, but still. Okay, so we're back to a metric space. I'm fixing it. I want to define things like open subset, closed subset. Okay. I take a subset. I'm going to call it open. If for any point in A, there is some radius r such that the open ball centered at A with radius r is included in A, such that recall that that was my notation. So a subset is open if, given any point in it, you can wiggle it around a little bit and you're still inside. Okay? And I'm going to call it closed okay, this is the fast way of defining it, if its complement is open. So what is the complement of a set? You have a set inside a bigger set, and you look at what is left behind. If its complement. So x take away a. Okay, so this is just x and x such that x is not in A, if this is open. Now, these two are the fundamental notions of topology, is what people would say. And of course, we've seen these words before, open interval and closed interval. And indeed, open intervals are open sets, and closed intervals are closed sets. Okay? Okay, so that's the interval from 1 to 2, endpoints not included. Okay? I'm saying this is open. Well, let's try to see why this should be the case. I'm saying if I were to take any point in my interval, let's say, so this is from 1 to 2, let's say I'm taking 1.5 in the middle. I'm saying I can find a radius such that the open ball of that radius, centered at this point, is inside, completely inside. Well, I can choose, for instance, r to be, what, 1/4? And there you go. Okay, that's the point. No, but here's an issue. For instance, if I were to take 1.9, it's all the way here. Now, if I were to use the radius, which for this we use the 1/4, now I'm leaving the set. Is that a problem? Exactly. You see, the quantifiers, the orders of quantifiers are important. I'm not saying that there is some r such that for any a that happens. I'm saying for any a, there is some r. R depends on a, possibly. Okay? So you have that control. What happens if I were to take the complement of this? Well, it's everything. So it's all the numbers that are either not more than 1 or not less than 2. So, or maybe we should start with this. If I were to take a closed interval, that's closed. In a second, I'm going to give a more convenient way of perhaps thinking about this using sequences, but let's first use this topology definition. So in order for this to be closed, everything except points in that set should be open. This is the same thing as saying that R take away 1, 2 is open. Well, what is this? This is minus infinity to 1, open, and then 2 to infinity. So this is minus infinity to 1, this open ray, and then union 2 to infinity. Well, both of these are open, and I hope it's straightforward that no matter which point I choose, either it's going to be here or there, and then I can apply the same argument here and sort of come up with sort of like a radius to stay fully inside here or fully inside here. Okay. Now, based on this, you should immediately start thinking about the other types of intervals, because we also have half open, half closed intervals and things like that. That really shows that a set might be neither open nor closed, or it could be both. Instead of saying half open, half closed, because in general, how are you going to say half, right? Like there's no side, you just have like the boundary, if anything. And so instead you say it's neither open nor closed. Why is this? Well, so now this side is open and this side is included. Is this open? Well, we're going back to the definition. I hope you can see immediately that if I were to take some point, some center inside, I would be able to find the interval. The problem is here. If I were to take any ball where center is 2, no matter how small I choose R, one side is going to escape. Okay? So the boundary problem, so the boundary point is a problem. So not open. How about closedness? For closedness, I'm going to look at the complement, right? So how does this look like? It looks like this. I want this to be open, and again, this is an issue. So some sets are open, some are closed, some are neither, and some are both. So I'm taking as a subset the whole thing, okay? That is both open and closed, right? Because if I were to take any number, obviously an interval, an open interval, which is a ball, is going to be inside. And if I were to take the complement, I get the empty set. But then an empty set is vacuously true because this is saying for any A in A. If there is no A in A, then it is true. Okay, this is like a silly thing, but it is true. So A is both open and closed. Some people call it clopen. I don't like that terminology. But okay. Any questions about these? Another example that is good is a finite set, let's say. Or you don't need to have a finite set, actually. A metric space with discrete topology or discrete metric. Any subset of any metric space with discrete metric is both open and closed. Is both Why is that? Because if I were to take the radius, if I were to take the radius small enough, an open ball would be just the center. And so I can just keep writing things then. Maybe this is an exercise then. Yes?
Can you remind me what it means to have discrete metric versus
Yes.
non-discrete metric?
Discrete means, so this is the distance between any two distinct points is 1, I'm saying.
Gotcha.
Yeah. Which means that relative to this, right? So if I were to take the 1/2 ball, this is nothing but the singleton. It is only the center. That's why it is called discrete. Okay. Any questions about these? Okay. Here's another characterization of closeness using sequences. Just like with continuity, oh, maybe I should add that as well. 2 exercises for you. We can talk about continuity of functions purely using open sets. F is continuous if and only if given any open set in the image, its pre-image is open in X. Okay, so how do you verify this? You say, let's say you're going to use the epsilon delta definition. You're going to take an open set. That means that any point in it there's a radius for any point in it, such that that ball is inside, and then you're going to look back at the pre-image of that open ball, which you're going to realize is part of this epsilon delta definition, really, if you sort of rewrite it using sets. And so what do I mean by this? It's a pre-image. This is not, I'm not really saying here that f is invertible. So this is the pre-image. Doesn't mean f is invertible. And so definition is this. This is the set of all those points in X such that f sends, so whose images are in V. So X in X such that f of X is in V. Okay, so somehow if you start using open set, it goes backwards. Later on, perhaps we'll spend more time on this. And the characterization for closedness is closed. So the definition I gave before was about what happens without A, outside A. This is a definition from within. A is closed if any sequence in A that converges to some point in X has in fact its limit in A. For any A bullet, so sequence in A, if a bullet converges to some point in the ambient space, then in fact that limit is in A. Okay. Just to give an idea as to why this should be true, let's think about a closed interval again. Okay, interval from 1 to 2 closed. So what I want is this. I want to show that this is closed using this exercise. I want to use this characterization. So if I were to take a sequence in 1 to 2 that converges to some place. Okay. So that's one side and this is the other side. And recall that the sequence was something dynamical. It has a time. And so that means that I'm always choosing points here. Keeps moving around. If the sequence converges to some point, what I can think is this. So think it the other way around. Say it's not in this limit, there's a limit, but it's not in A. Let's say it's like to the right. Somehow the sequence eventually converges to this point. But this cannot happen, right? Because by definition of convergence of a sequence, it must be the case that after some finite time, my points should hit an arbitrarily close interval around this. Which means that eventually it's going to exit. Which means that the only way a sequence can converge inside 1 to 2 is that the limit is inside it. It cannot be outside the limit. That's the point. Okay. Okay, open, closed. Any questions about these? Open, you should always think about open intervals, closed intervals. Okay. Okay. Let's look at the next item. A subset is dense. Oh, okay. Let me introduce these things. Interior enclosure. I take an arbitrary set. It turns out that there are ways to come up with open sets and closed sets related to A. The interior which some people denote like this, A to the circle, or some people write int of A, is the largest open set inside A. So maybe I should write it like this. Okay. I'm just going to write it in words. Subset in A. And then the closure is the smallest closed set that contains A. So you should think of the interior as you take your set and you sort of like take a point in it and you sort of start blowing a bubble, and the largest bubble you take, that's your interior. And the closure is you sort of wrap your set into sort of like some shrink wrap, and then you vacuum it, that's the closure. Okay. Again, some people write like close of A, or you might see A to the bar. Smallest closed set containing A. Examples. What is the interior of this half open, half closed interval?
Open 1, 2.
Right? So this was the issue. And so what is the largest open set inside this? Open interval. Okay. What is the closure of that? So this and then close. What is the largest closed set that includes 1 to 2? 1 open, 1 closed, 2 open. Yeah.
Oh, I had a question about something else.
Yeah. Ask.
Okay. So how are you defining size for an open set? I mean, is that the largest R that you can choose for a particular point A? Does A not matter as much? Choosing this largest distance between them?
Well, you know about GCDs and LCMs from number theory, right? You say something is the largest if it's like, what is the LCM of 10 and 15? Largest common multiple. 15. So 30, I think, right?
Yeah.
Because this is like 2 times 5, and this is 3 times 5. So that means that we need to have 30, which means that this is some number that is larger than both, that both of these divide. And then if there were some other number that does the same thing, that's larger. Sorry, this is least common multiple. Okay. Again, 30 is a common multiple of 10 and 15. And among all common multiples of 10 and 15, this is the smallest. Okay? In the same sense. Now, what does it mean for sets to be larger or smaller? One is, that's a larger set now. Okay? Now from that, it's an exercise to construct what it means to be large and small. Okay. Yes?
The notion of like large and small changes though if you like change the metric, right? Like,
no.
If you have a more
No.
complicated space.
That is true, but this is like a set theoretical thing. Yes. Yes.
A way that I'm thinking about that might help is that like I'm breaking it down to its primes and thinking about like, okay, if you took those primes as a set, what is the smallest set that contains all of those primes? So it would be 2, 3, 3, and 5. And then when you multiply out 2, 3, and 5, you're getting 30. So if you break down the least common multiple thing into sort of like, okay, now we're just trying to gather up primes, sort of how you would approach it in number theory, that's how that makes a little bit more sense to me.
That might be a good idea, but the one problem with that is that now you need to define what it means for a set to be a prime set.
True.
Okay, so that's an issue. Maybe I should have just said it. So for instance, I would define the interior like this. I can write it. Let's say U such that U is in A and open. The union of all those open sets inside A. It turns out that this is an open set. Okay, and the other way around, sort of for the smallest, you're going to take an intersection. Let's try it. F okay. I guess now it's an exercise to verify that this is an open set and this is a closed set. It's one of the axioms, it turns out, that any union of any family of open sets is open and the intersection of any family of closed sets is closed. These things you learn in a topology class, but I'm being super fast about this stuff. Okay. Any questions about these? When it comes to topology, at least in the beginning, it gets scary. It becomes like syntactic. All you're doing is like logic, in a sense. But okay, so let's get back to this. What is a closure? What is the smallest closed set that includes 1 to 2, 1 included, 2 not?
We'll just do 1.
Let's just 1, 2, close.
Yes. You have to have everything already.
The intersection of everything.
Well, intersection of everything that includes the whole thing.
Oh.
So it includes at least this. Yes. Okay. Good. A is dense in X if its closure is everything. Okay, which basically means that any point in X can be approximated arbitrarily close using points in A. So can approximate any point in X via points in A. An example, of course, rationals is dense in reals. So rationals closed becomes R. Okay. Good. Now, here are more important topics or words, at least for us. So the next definition is something called compact subset. It's a definition for a compact subset, because the idea is that we would like to be able to distinguish this and this without using lengths and stuff like that, just their general shape. So this is just an array that starts at 1, goes to infinity, and this is the closed interval. Both of them are closed sets, okay? Both closed. We're going to call this, so a closed interval with with finite length, let's say, even though that's not going to be the actual definition. That's going to be compact. This is not going to be compact. It goes off to infinity somehow. Cantor set 2 is going to be compact, by the way. It's going to be closed and compact. So, definition. Understanding the definition of compactness is, it takes a while compared to even open and closed. There is a definition using open sets and covers. Let's not talk about that now. Let's look at let's use a definition in the book. Compact if for any sequence a bullet in A, it's going to be something stronger than closeness. Okay? This sequence, any sequence, has a subsequence that converges to some point in A. There's a subsequence and a point such that A prime infinity, A prime bullet converges to this. Okay. Now note that this definition does indeed distinguish the two. Maybe it is perhaps hard to see why this should be compact using this definition, but certainly you can see why this should not be compact. Because I can take as a sequence 1, 2, 3, 4, 5, 6, and so on. And if I were to take a subsequence of it, I don't care which subsequence, so I'm sampling. There's no way it's going to converge to anywhere, okay? Because infinity is not in this interval, okay? We should think of it like that. Questions? This is a lot to take, I realize. Like I said, like each of these words probably deserve its own 2 weeks in another grad class, but for now, just like understand that there's a bunch of terminology that governs everything, and as you sort of like start reading other things, you're going to have to sort of get comfortable with some of these ideas. Okay. Oh, 2 more. These are relatively easier definitions, actually. Boundedness and total boundedness. Or even before that, perhaps, this is a nice exercise. If I were to take an open ball in any space, close it. That's the open ball. If I were to close it, I would just get the boundary as well. Okay. And likewise, if I were to take this set, take its interior, I would get the open ball. Barnsley gives a couple more definitions, things like limit sets or limit points, boundary, blah, blah, blah. Let's not get into that. I don't see that we're going to use them, but if it turns out that we're going to use them, we can sort of get back and define them as well. So now these are 2 metric definitions. So that requires a metric. A is bounded. Well, if it is included in some sufficiently large enough ball. If there is an x0 and x and an r radius such that A is included in here. Basically saying that this is my set. So if I were to take large enough closed or open ball, it doesn't really matter there, that I get to contain all of A. Okay, this is relatively easy to understand compared to compactness, for instance. There's a stronger definition which is called total bounded or totally bounded. And here's some math syntax. Whenever you see something like this, it's like, oh, it's bounded, but perhaps like it's total means it sounds like it's stronger. And it's going to turn out that indeed totally bounded implies bounded, but not necessarily vice versa. If instead of trying to bound A using one large ball, you can bound A using a couple of small balls for any precision. If for any epsilon there is a finite subset f of A such that if I were to take the union of all those balls of radius epsilon centered at points in F, I get to cover A. And in our notation, this is what that means. So this is bounded. Totally bounded means so you have your set here, and you take a precision. This is sort of like your pixel size. Imagine it like that. And you're trying to cover A using pixels of size epsilon at most. But you get to do this for any epsilon. So you get to choose, you get to shrink all of them. Quite possibly this finite set is going to change. Maybe you're going to have to take more centers, but still you get to cover using finitely many open balls. Okay. I think we should take a break. And then when we come back, we're going to keep working on these. 5-minute break.
Being totally bounded.
Oh, yes.
Would that imply compactness then?
No.
It would not. Okay.
We'll see in a second. You're asking the right thing. Now, here is where things are going to get slightly more complicated. Because ultimately, we're using metric spaces and these metrics and stuff like that. And when I'm drawing pictures, I'm basically pretending that everything is the plane and somehow things work. But things are not as simple as that. And a metric space is a much more general structure. The mystery there, of course, is that figuring out when you can think of this abstract metric space as basically the plane and sort of like think using a caricature, and then you cannot. And this is an instance where things are getting complicated in this sense. If you were to take any metric space, X, an arbitrary metric space, and if you were to take a subset A of it, if it is totally bounded, it is also bounded. So if you can cover A using finitely many small balls, you can cover it using one large ball. Okay, it's clear in this picture, but I'm saying it is true in this abstract setting using only axioms. This is a very good exercise. This exercise that I didn't write, I'm going to write now. The converse is also true if your metric space is Rn. So if you were to try to imagine this difference between totally bounded and bounded using the plane and stuff, you wouldn't be able to really see the difference. Okay? Now let's think about this exercise a little bit. Why it should be the case. And as usual, I'm sort of like thinking about it using r to the 1, right? The real line. So the intervals and stuff. So for instance, if you had an interval, I don't really care if it's open or closed, but I want it to be bounded. What does that mean? It means that it has finite length. It doesn't go off to infinity. So it's not a ray. So it's going to be, so your A, oh, let's write it like this. You can also use this if you want. This means I don't even know if it's open or closed because it's not going to matter. So the point here is that it is an interval of bounded length or finite length. Certainly this is bounded. Right? Because A is somewhere here. Either 0 is here or here or here. I don't really care. 0 is somewhere, right? I say that 0 is here. And if I were to take my large ball like this, I would cover everything. So it is bounded. But also it is totally bounded. Because if I were to take an arbitrarily small epsilon, well, what I can do is I can look at epsilon over 2 balls in R, which are intervals of length epsilon. And I would just partition this, right? So if this is like this, let's say, this is A, this is B. So the length is B minus A. We can come up with sort of explicit numbers here, but the point is that you can partition this as small as you want. So it is also totally bounded, okay? For a general metric space, it turns out that this is not true. So there are subsets of certain metric spaces that are bounded, but not totally bounded. Still, it's a thing, okay? Oh, and then the third exercise, this is also very nice, very illuminating. If I were to take any metric space and 2 subsets of it, such that one is smaller than the other one, well, if the larger one is totally bounded, so is the smaller one. Now, when you think about this exercise, the problem is that when I'm trying to totally bound this smaller set, I need to use centers that are in A. But B being totally bounded says you can cover B using balls whose centers are in B. But some of the centers, perhaps, that are here are not here. Okay, so that's the issue. How do you come up with a total bound using A, using points in A? It's a very nice exercise. Any questions about these? Now, one of your colleagues, right after we had the break, mentioned something, and that's along the lines of what I wanted to prove. That's our first big theorem in this class. I hope I'll be able to finish it. And it's a certain factorization theorem. Not the factorization of numbers or something, but factorization of concepts. Compactness is so important that we would like to be able to factorize it, meaning that we would like to be able to come up with some other conditions that, when all together are satisfied, is equivalent to compactness. So here's what I mean. Theorem. Let X be a complete metric space. The moment you see this word, you should immediately think about Cauchy sequences and convergent sequences, and recall that complete means Cauchy implies convergent and vice versa, of course. So somehow, whatever is going to come after this, this hypothesis, it has to, so probably in the proof I'm going to try to use, I'm going to try to come up with a sequence that is a Cauchy sequence, and then I'm going to say, oh, but the space is complete, which means that it converges somewhere. Okay, that's how I'm going to use this assumption. I didn't even state the theorem, but that should be your reflex. And let A be a subset. Now this theorem gives a condition. It factorizes what it means for A to be compact. You can go through the definition, of course, in general, but sometimes using the definition is not convenient. So you come up with some technology, some theorem, and that tells you, oh, instead of looking for the sequence and then the subsequence that converges, blah, 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 I'm just going to do these other things. Then A is compact if and only if it is closed and totally bounded. So you see, this theorem factorizes the notion of a subset being compact into the subset being closed and totally bounded. Two distinct notions. Okay, that's what I mean by factorization. Now, adding this exercise to this theorem, we have this also. So let me write it immediately. Corollary. A subset of Rn is compact if and only if closed and bounded, because totally bounded in Rn is the same thing as bounded. So it's more manageable, perhaps. If and only if it is closed and bounded. And this is a corollary of this theorem when you use this exercise. It literally allows you to replace totally bounded by bounded. Okay? So our aim is to prove this theorem. Any questions so far? So how do you show an equivalence? You say, okay, if I were to assume A is compact, I want to be able to show that it is also closed and totally bounded, and vice versa. And then, I'm going to say, I want to go backwards. I'm going to assume a subset A is closed and totally bounded, and somehow I'm going to try to come up with some argument that says that it is compact. Okay. Oh, this exercise here, that total boundedness is inherited by subsets, is going to come in handy in this in the proof of this theorem. Proof. So now I'm trying to go that way. I assume that A is compact. I want to show that it is closed and totally bounded. Going forward, probably I'm not going to be as formal and I'm not going to be as explicit when writing proofs. I'm just going to say them out loud and stuff. But for now, let's try to be slightly formal so that we have some experience. So the definition for compactness holds for A. If I were to take a sequence, there is some subsequence of that sequence that I chose that converges to some point in A. That's what I assume. Want two things. I want that A is closed and that A is totally bounded. Well, instead of proving both of them at the same time, the point is you prove this and you prove this. Okay? One. So this is what I want. And what does that mean? That means, based on the definition, I can use that its complement is open and stuff like that. But let's use the sequence definition. I want to take a sequence in A that converges to some point in the ambient space X. Okay. X infinity in X such that a bullet converges to X infinity. Okay? In order for A to be closed, this should mean that X infinity, this target, this limit, is in fact in A. So once. You see, I sort of like try to open up the definition of something, and I keep sort of reminding myself, what am I trying to do? And I keep sort of like unfolding things. Want. This is what I want. If this is the case, that's the definition of closedness. Well, there's one thing I can use, that A is compact. A bullet is a sequence in A. That means that there's a subsequence of A, bullet, that converges to some point in A. There is some subsequence of A, bullet, which is A prime bullet, and there's a point A infinity, prime let's say, in A such that A prime bullet converges to A prime infinity. Okay? Now, the original sequence from which I sampled this A prime bullet already converges somewhere. And if you're sampling a sequence that converges, that sample should converge to the same point, which means that, in fact, this A prime infinity is actually this point, the target that I already had. But then, this is this, and it is already in A. Okay? This is like a silly logical argument, but this is how you do math. Okay? Any questions about this? Yes?
When we're writing arguments like this in the future, will we be expected to go back and like cite a theorem that says if a sequence or a subsequence of a sequence converges to A, then the sequence converges to A? Or is that something that we can just kind of run with in this class?
Probably you can run with it.
Okay.
Yeah. I mean, it depends on the rest of the report that you're writing, right? Like, because like if you're having troubles with sort of something comparably hard, then probably you want to cite the other thing.
Yeah. So just use your own context.
Yeah. You need it to be consistent. You want your level to be consistent, basically. Yeah. If it's obvious to you, you can just like skip it, but then probably other things should be obvious too. So, and all that. Any other questions? Okay. Oh, I'm erasing because I don't have any more space. But so closedness, we proved. Now we need to prove total boundedness. Okay. So for any epsilon, I'm going to take an epsilon. I need to find a subset that is finite in A, such that the union of balls whose centers are in this finite set covers everything. Now, when you think about this, how do you even come up with that set? It's sort of like a constructive thing, perhaps. So the trick there is to say it's not totally bounded and come up with a contradiction, okay? Now there's a let's say, discipline or way of doing math, which is called intuitionistic or constructive math, which would not accept this proof, but for us, we will allow it. Because the class is already too complicated, I think. So say it is not totally bounded. I already assumed that A is compact, but say somehow it fails to be totally bounded. So let's write down the definition. For any epsilon, there is a finite set such that the epsilon neighborhood or collar of the set contains everything. This is the definition for total boundedness. I'm saying say it is not, which means that you need to put a not here. And so there's some logical algebra going on here. Whenever you have a negation of a statement, all you do is you turn for alls into there exists, and there exists into for alls, and then ultimately you turn this the other way around as well with the same orders. So this is the same thing as saying that there is some epsilon such that for any finite subset, this ball does not cover A, which means that A has a point that is not included. A take away this is not empty. These two statements are logically equivalent. Okay? So this is sort of like some small error margin. Okay? It says that there is a small error margin such that no matter how many finitely many points I choose, there's always some point in A that I keep missing. Okay? So now I can start taking points in X, points in A. So using this statement, I'm going to construct a sequence. Let X1 in A. And let me let my finite set to be that singleton set consisting only of X1. Let me call it F1. By this condition, there is some point X2 in A that is not this. Okay, so now apply the same thing. Now your finite set is going to be X1 and X2. Okay, you're going to keep taking more and more points. Now, iteratively, you can keep going no matter how many points you chose, right? Ultimately, this gives you a sequence. Gives a sequence. X bullets in A. Do any of you see the conclusion from here? Let me draw a picture. Yes.
Don't we know that it's gonna, like, the sequence is gonna converge in A? That's, or it's gonna converge, so it's gonna be bounded, like, since it's converging to a finite point.
It's almost the idea. Think about compactness. So first of all, can the sequence converge to anything? Here's a picture. Recall that this is still the assumption. We proved closeness, so I'm deleting that part. So here's my A. And I start this induction argument like this. I take 1 point, X1. I'm saying, of course, this should be F1, F2, and so on. If I were to take the epsilon 0 ball around X1, there is some other point x2 in A outside that ball. So I take this small epsilon naught ball, that was my F1, everything inside included. This step is saying that there's some x2 outside that ball. Let's say it's here. Now you go to the next stage. It says if you were to take the epsilon naught ball around x2 too, there's yet another point somewhere. And you keep going like this. And you get to do this as many times as you want. Because for any finite set, this holds. Now that means that this sequence, x1, x2, x3, and so on, cannot converge to anything. Because they cannot approach each other. There's a lower bound as to how close they can be. And furthermore, if I were to sample so that I have a subsequence, well, the same thing is true for that as well. That means that this sequence does not have any subsequence that converges. But that contradicts with compactness. M at least 2 epsilon 0. So subsequence in A or otherwise. That contradicts with A being compact. A contradiction. So the idea is that if you end up with a contradiction, that must be that along the way you made a mistake. And then you say, I didn't make any mistakes except in the beginning, which means that this must be false. If I didn't assume this, I wouldn't be able to come up with this contradiction. Questions about this? Okay, this is one side. You see, we assumed A is compact. In this board previously, we showed that A must be closed. And then now we show that A must be totally bounded. So compact implies totally bounded. And furthermore, when you think about it, I'm actually not using that X is compact, X is complete. There was no Cauchy sequence whatsoever in this argument, which means that this is actually true for any metric space. That means that going the other way around, somewhere I should be using completeness. We don't have time because the other way around is more complicated than this side. So next time we're going to start doing that. But let me just write it over here. This direction. So totally bounded and closed implies compact. We're going to show this statement next time. And there we're going to use completeness. Any questions? I have a couple minutes, but not enough for doing this part. So you see, one part of writing arguments is, being formal and stuff like that, but there is sort of like an accompanying part, which is the geometry. Somehow you get to pretend that it's Euclidean, it's the plane, but you need to always keep in mind what the axioms are. Okay.
So, okay, I have a logistics question that is
Yes.
not related to this, but specifically about weekly reports. Because
Yes.
I want to cite something we did in class. If I just said from the lecture on 8.
Yeah, you can do that.
That
Yeah.
works, okay?
Yeah.
Awesome.
Tied to that a little bit, is it necessary that we have references if we're just...
No, not necessary. Yes.
This is more about the argument that we're
Yes.
constructing. Looking backwards, just from it looks like this set up a fairly nice way to do the backwards with the open ball definition of compact.
Maybe.
If like, is that a way that you would see being reasonable?
Yeah, yeah. I mean, ultimately they're equivalent, but
Yeah.
Yeah. Yeah, I would say so. Any other questions? But one thing is that because I'm ultimately going to use compactness, this is about this uniform context. That's like one thing that you should keep in
Being able
mind.
to translate between contexts.
Yeah, yeah, yeah. Okay, good. Thank you. Have a nice weekend. I'll see you next week.